All right, welcome to 40 Minutes of Competence by the Amber Book. And for today's problem, you're employing a cut and fill strategy, a balanced site strategy, whereby the earth you are using as compacted fill behind a retaining wall will come from active excavation for the building's foundation. The question is, how much compacted soil will be available for the retaining wall? And we're given that we have 230 banked cubic yards of earth that are going to be removed for the foundation of the building. And then after excavation, that becomes 300 cubic yards of loose soil on the pile. And the swell factor for the soil is 10%. And this is a little bit tricky because you actually don't need that amount of information, and it's a bit, it's extraneous and might even have confused you, but that was intentional. So let's go ahead and go through this. If we're going to start with soil in its undisturbed state, in its what's called its bank state, we would have 230 cubic yards that we're removing from the foundation. And so graphically, here's the proportion that's air and water and soil and rock. And then when we're going to pile that, we're going to have more air, and there's going to be more kind of space between the rock. And so we wind up with 300 cubic yards of loose 300 loose cubic yards of soil. And our answer is going to be 253 cubic yards of compacted, because we're going to take that loose soil and we're going to bring it over to the retaining wall, and then we're going to compact it down. And so that's where our 10% swell is going to come from. And we'll go through this numerically, but I want you to own it conceptually before we do. You know I'm all about that. So it's going to swell 30% from its bank condition to its loose condition, because we were given that it goes from 230 to 300. But when we're talking about swell from its bank condition to its compacted condition, in this case we have 10% swell, so that 230 is going to become, well, 10% of 230 is 23. So 230 plus 23 is going to be 253 cubic yards compacted. Now let's go ahead and talk about that more. We have bank measure, we have a loose measure, that's when it's on a pile, and we have compacted measure. And when we go from bank measure to loose measure, it's always getting fluffier. And when we go from loose measure to compacted measure, it's always getting less fluffy, it's always getting more compacted. But when we go from bank measure to compacted measure, it's usually getting more fluffy, but not always. And we'll get into that in a minute. So we're talking about site, and generally we want to balance our site, because if we have waste, that means we're going to have to haul that waste away, and it turns out that's really expensive. Many of you guys are at least familiar with the project by David Adjaye, the project on the National Mall, the one focusing on the history and culture of African American culture in the US. And they excavated so much site that you could take all the dump trucks. If each dump truck load was backed up one to the other, nose to tail, it would extend from DC into through Maryland and into the Pennsylvania border. So removing soil just takes a long time. And when we remove it, we'll often pile it up, and then it'll take up more volume when we pile it up. But then, maybe there's rain and wind, and depending on how long it's there's some erosion. But generally, it will still be much fluffier. The stuff we remove from here will be much fluffier, or I should say the stuff we remove from wherever we removed it here will be much fluffier when it's piled up here. But then after that, we're going to compact it. We're going to run a compactor over it, and then it's going to become more compacted. So we're given that what we just know from the nature of swell, that if we take our compacted cubic yards, to calculate that, we take 100% plus our swell, and we multiply that by our bank cubic yards, and that's how we get our compacted cubic yards. So our compacted cubic yards is going to be 110% times the 230 cubic yards that we removed for the foundation, and that means that's going to give us 253 compacted cubic yards behind our retaining wall somewhere else on the site. As always, don't just look at that as a number. 253 is bigger than 230 by about 10%, and it's because we've dug it up and made it more loose, and then compacted it down, made it tighter, but not as tight as it was when we took it out of the ground. All right, now, this is your next problem. Go ahead and answer this. I will give you 90 seconds to go through this one. No, I'm gonna give you 2 minutes. I'll give you 2 minutes to go through this one in silence. All right, so in this case, I'm looking for the swell that's involved going from bank condition to loose condition. So the kind of intermediate condition when we're going to pile it up in the site. Generally, architects don't deal with this. Generally, this is something a contractor might deal with. But in a contractor's world, if you're talking about swell, you might have to specify, are we talking about the swell between the bank condition and the final compacted condition, or are we talking about the swell between the bank condition and the loose condition? And so here we were given originally that we had 230 cubic yards of earth in the ground before we dug up our foundation, and after excavation that became 300 cubic yards of loose soil. And so we can say, okay, our 300 loose cubic yards is equal to 100% plus the swell times our bank cubic yards, and that winds up being a 30% swell factor. So if we take 230 bank cubic yards, we multiply it by 1.3 because that's 30% swell, we're going to then get 300 loose cubic yards. So our swell factor, not so relevant for architects, but relevant for kind of understanding that there are two different flavors of swell factor. There's swell factor between bank and loose when we dig it up first, and there's swell factor between bank and compacted. There is not swell factor that we usually use between loose and compacted. All right, so that's where we get this 30% swell between the 230 cubic yards in the site and the 300 cubic yards loose. I know this is not difficult. Just trying to do it enough times that it becomes second nature should you see a question like this on an exam. All right, this is the next problem. Here you're employing a cut and fill strategy, same as before, whereby the earth you're using as compacted fill behind a retaining wall will come from excavation for the building's foundation. How much excavated soil will be needed for the retaining wall? In this case, we're not taking out 230 cubic yards for the foundation. In this case, we require 230 cubic yards to create the retaining wall. The swell factor is still 10. So now the question is, how much soil do we have to remove from the foundation to achieve 230 compacted cubic yards and behind the retaining wall? Again, for 2 minutes, I'm going to go ahead and let you work this out on your own. All right, so what's this? Well, it's pretty straightforward. The compacted cubic yards, that's what we have at the end, is equal to 100% plus the swell factor times the bank cubic yards. But this time, instead of being able to fill in this, we're able to fill in this. So 230 equals 110% of what? 230 equals 110% of what? So we can divide 230 by 1.1, and we get 209 bank cubic yards. So again, that's not just numbers. What does that mean? That means if we want the same soil, if we need 230 cubic yards compacted behind the retaining wall, we're going to have to dig up 209 cubic yards in the foundation and bring it over to the retaining wall. And that's going to become more and then in the pile, but then less once we compact it down. And so when we think about balancing a site, and we think about kind of balancing out cut and fill, I think normally we think, okay, if we want 230 cubic yards of fill, we need to cut 230 cubic yards. But what we're saying is that balance line is not always in the middle. In fact, it usually is not. So if we don't want any waste or borrow, we don't want any extra soil that we need to get rid of, or any extra soil that we need to haul in, which is, like I said, extremely expensive, surprisingly expensive, then we want to balance it out. And in this case, because we know something about the soil, it requires 209 cubic yards of cut to give us 230 cubic yards of fill, because the swell factor is 10%. So that balance point, that kind of tipping point, that fulcrum, is going to be a little bit off, a little bit off the center relative to what the swell factor is. All right. So, next question. How many cubic feet are in a cubic yard? If no one's around you, go ahead and say it aloud. If someone is around you, go ahead and write it down or really commit to something. The answer, of course, is 27, because a cubic yard is 3 feet by 3 feet by 3 feet. And so it's not 3 cubic feet in a cubic yard, it's 27 cubic feet in a cubic yard. And it's very easy, it's a very no-duh statement, but if you're in an exam, it's very easy to mess it up, because it's actually quite likely that both in practice and in the exam, you're going to have to move back and forth between cubic feet and cubic yards, whether it be in concrete or fill. All right, next question. You're employing a cut and fill strategy whereby the earth you're using is compacted fill behind a retaining wall will come from excavation for the building's foundation. Same as before. How much compacted soil will be available for the retaining wall? So now we're asking how much compacted soil will be available for the retaining wall if we're given that we have 230 bank cubic yards of earth removing from the foundation. So we're back to the beginning, where instead of requiring 230 behind the retaining wall, we actually are going to be removing 230 bank cubic yards from the foundation. And in this case, the shrink factor for the soil is 10%. So it's not swell factor, it's shrink factor. So I'll give you 2 minutes, go. All right, so what do we got? Well, again, we're starting with 230 cubic yards. It's given that when we pile that high on the site, waiting for it to be brought down to the retaining wall, we're going to have 300 cubic yards of loose soil, so that's a 30% swell factor. But in this case, when we go from here to here, which is always how we measure swell and shrink, we always start with the bank measurement, and that's our reference. So we can go from here to here and talk about swell, we can go from here to here and talk about swell, or we can go from here to here and talk about shrink. And in this case, it's shrink, which does not always happen, but it does sometimes happen where the compacted soil is actually tighter than the bank condition of the soil, which seems kind of weird to me too. I actually called up a couple of civil engineers around here where I live in the mountains of Virginia, and I said, what's the normal? And they said, oh, it's always swell around here. It's always about 10% swell. But it can be 10% shrink, it could be 30% swell, it could be 25% shrink, whatever. There's all kinds of ways where it actually may be that the compacted value is actually going to be smaller than the bank volume, because just I guess Mother Nature doesn't quite, maybe it's a sand dune or something like that where you brought the soil from, and Mother Nature doesn't compact the sand dune that well. It's pretty loose, and we can compact it tighter behind our retaining wall. So in this case, our answer is going to be 207, and let's see how we got that. We said, okay, our compacted cubic yards is equal to 100%, in this case minus the shrink factor of times the bank cubic yards, and our bank cubic yards is 230, and our shrink factor is 10%, so our compacted cubic yards is going to be 90% times 230 cubic yards, or 0.9 times 230, and that's going to wind up with 207 cubic yards. And what does that mean? Well, that means we're taking 230 cubic yards out of the foundation, and after we've compacted it down, it's actually smaller than Mother Nature had it. It's actually at 207 cubic yards. And so we say we have a 10% shrink, because we're always starting with our bank measurement when we're figuring it out. So loose soil is always more fluffy than bank soil, and compacted soil is always less fluffy than loose soil, but compacted soil may actually be less fluffy than bank soil, or may not be. And so you're going to want to kind of understand that, but it's pretty straightforward. Again, this number here could be smaller than this, or it could be bigger than this, just depending on the nature of the soil and the nature of how long it's been eroding and so forth. So if you have, in each case, we're going to start with a cubic yard of bank, one bank cubic yard of soil. So if you're talking about granite, a cubic yard, once we go to loose, becomes 1.7 cubic yards. So once we pile it on the site, once we blast it out and pile it on the site, it's 70% bigger. And so our swell is going to be 70%. Then when we compact it down, it's going to be 1.4 cubic yards. So it's going to be smaller than the pile, but it's going to be bigger than what we started with. And so you can see it's grown by 40%. So our swell is going to be 40%. Our swell is going to be 40%. Now for limestone, it's pretty similar. We can start with a cubic yard, and when we blast it out and pile it up, it's 1.6 cubic yards. So we've increased its volume by 60%. And then we're going to compact it down somewhere else on the site, and now it's 1.35 cubic yards. So we've had a swell factor of 35% because it's 1.35 on the retaining wall where it was 1 cubic yard on the foundation. All right, but we can go the other way. So if we have pure clay, it may be that we have 1 cubic yard of one bank cubic yard of clay, and we're going to dig it up and pile it, so now it's 1.6 cubic yards, so we know it's going to be a 60% swell factor. But that swell factor is bank to loose. Bank to loose. But from bank to compacted, we're going to wind up actually with a shrink factor, because that 1 cubic yard has then become 0.9 cubic yards, which means we have a shrink factor of 10%. Now, I've written it here as negative 10%, but that's a negative 10% swell. Really, what we would call it on the site or in our meetings with our subcontractors, we would call it a 10% shrink factor. A 10% shrink factor. And that would let us know how we can balance the site, and we can flatten it out for a driveway or flatten it out for a plaza or something like that. Likewise with sand, we can start with 1 cubic yard. It becomes 1.1 when it's piled up high, and that's only a 10% swell factor from bank to loose. But when we go from bank to compacted, it goes down again to 0.9 cubic yards. So again, we have a shrink factor of 10%. We wouldn't say we have a shrink factor of negative 10%, but that's just the way I chose to show it on this chart to differentiate swell versus shrink. So now our shrink factor is 10%. All right, last time we met, so we had a question. Someone said, "What's it called? What's it called when we, what's this thing about return air drill coming at the same time as on either side of our light fixture?" Because I was talking about sucking the air across the light fixture. Well, let me show you what it might look like. So in this case, it's a light fixture. The light fixture is the plenum. The light fixture is the plenum, and the air is allowed to go next to the light fixture. I'm sorry, the light fixture is in the drop ceiling. The air is allowed to go into the plenum right next to the light fixture. And the idea was, and I say was on purpose, was that we have a hot light and we have to return air anyway, or maybe we have to exhaust air anyway, and we're air conditioning the space, so we want to take that warm room air and we want to either send it to the perimeter where maybe it's cold because it's a cold day, it's a cool day, and maybe the center of the building needs air conditioning, but the perimeter needs cooling. So we may redistribute the warm air from the core to the warm room air from the core to the perimeter, or we may exhaust it, or we may just send it back through the air handling unit to cool it off again. But either way, the idea was for this type of luminaire, and I have the name, hold on one second, I forgot the name of it. I'm gonna look this up. But we have this, it's just kind of a concept that frankly doesn't exist outside of mechanical and electrical equipment for buildings, or not in a meaningful way. So it's not really a thing. It's called a heat of light fixture. That's what it's called. Heat of, I don't think you have to memorize that, but that's the name of it. And they never really took off. So in an older version, and maybe the current version of mechanical and electrical equipment for buildings, what those who have been studying for a while and know what they're talking about call mead. And this may have been your textbook in school. There's actually a rap, and you can do mead rap, and you can go on YouTube and find the fairly decent, surprisingly decent rap that a student made about mead. But anyhow, the idea is that the light is hot anyway, the fixture is hot anyway. So if we're going to take air out of the building on a hot day, we may as well cool the light so that it doesn't add convective heat to the room by warming up the air around it. And if we have to exhaust the air anyway, we might as well exhaust the hot air that runs across the light. In reality, since Mead published this, lights have gotten much cooler and they're more efficient, much more efficient. And this concept never really took off. So it's kind of one of those things where it's only a Mead thing. I have no way of knowing if it's in the test or not. But if someone had asked about it, that's why we're talking about it. Now there's another version that's also in Mead that talks about warm air going in as a supply, and then coming out, and being heated. And this is for a cold climate or a cold season. So if we're bringing hot air anyway into a space, the idea is again that we could run it across a light fixture, and we could take some of the heat from the light fixture and use it to reheat the air because maybe it's lost some of its punch as it moved from the air handling unit and got cooler as it moved through the building before it hits its eventual diffuser. But in reality, again, these are kind of dated ideas and are really no longer relevant. All right, now this is our assignment for next time. It's a little bit different than we've usually done. We didn't get to have March Madness basketball this year, but in lieu of that, we're going to have Building System Madness. And this is our final four of building systems. So there are seeds, and these are all different concepts in building systems, sustainability or plumbing or electricity and so forth. And what happens is there's just this kind of greenwashing that you guys are all familiar with that's kind of washed over the architecture industry, where people just say it's green because maybe it does 2 or 3 of these things, or maybe you found that you're not sure where to begin. It's intimidating, and the truth is that every one of these on this list, all 64, and I could probably come up with another 10 off the top of my head, and another 30 if I kind of thought about it for a while. These concepts are each one of them is the topic of, or could be the topic of dozens of PhD student dissertations. So there's a lot to know, and so it's unrealistic for you to do all of this for your building because you have only so many hours. So what I've done is I've put them in kind of a default seating. So energy use is number 1, and a ground water loop is number 16, and so forth. So if you have window shading is number 6, it's probably going to be ceiling fans. But if you're in a humid, cloudy climate, maybe the ceiling fans will upset window shading. But if you're in a normal climate, or your client isn't particularly enamored of ceiling fans, then window shading will probably beat the ceiling fans. And carbon footprint is a number 1 seed, energy use is a number 1 seed, construction cost is a number 1 seed, and the architect's design time is a number 1 seed. So these are the things that are kind of often going to wind up being the most important generically. But if you have a particular building where you're doing an arboretum and tree shading becomes important, or you're doing an allergist office and low off-gassing finishes are important, then there may be an upset. And you're going to find a lead 8 or a final 4, and those are the 4 or 8 things you should be focused on. So that way you can spend your design time on the things that are most important. And so what I want you to do, I'm going to send it out. If you're not already on our mailing list, get on it by emailing firms@olive-book.com. And we'll send you out a instruction packet that has this, and you can print it out. Or you can, let's see if I can erase all the yeah, I can't do that. Or you can just take a photo of this right now and print it out later, but you'll do this for your design project, and then it will help you. It'll do 2 things. One is it'll help you to It'll help you to prioritize, because that's really the game, right? The goal isn't to do a little bit of everything. The goal is to do a few things right, and then you have those in your pocket for your next project, and they'll become easier. And so your vapor control and your blocking wind in winter, maybe you're in a warm, humid climate, so vapor control upsets, or maybe you're in a cold, windy climate, in which case the favorite blocking wind in winter would win. And so then next week, we're going to start 10 minutes late instead of 5, so we'll start at 2:10 to give those who didn't do it beforehand a little bit more time to do their bracket. And then I'll go over things like groundwater loop, some of the things that maybe you don't know. So come with questions if there's some things that you don't know. What does a smart thermostat mean? Why do we put argon in the window cavity, etc.? Because I'm not going to have time to go over all these, but I would love to focus on the ones that you're most curious about. So we'll do that next week. So anyhow, we're going to send out our normal weekly email, and that email will have a link to a clean copy of this, or you can take a photo of it and just do it on your own. All right, we're going to take 30 seconds or 10 seconds while I kind of straighten out the electronics and the software, and then you guys will be able to ask me questions.
Why are argon necessary in a window?
So in an IGU, which is basically a double pane window, so here's our window, and here's our second window, and then we have it sealed off at the bottom. So here we're looking at it in what could be planar section. And typically what we'll have, if we don't have argon, of course there'll be air in between. The problem with air in between is twofold. One is air is a better conductor than argon. So if it's 0 degrees outside and it's 70 degrees inside, if there's air in there, there'll be more convection going across that gap with air than argon, because argon just has properties that make it less efficient at transferring heat across, which is good. Less efficient in this case is good. We want it to be less efficient in transferring heat so it can be more efficient in insulating heat. And then also, argon doesn't have moisture. Argon doesn't hold moisture the way that air does. So if there's going to be condensation, if there would have otherwise been condensation, it won't happen if there's argon. Now, over time, sometimes there'll be leaks and air will come in anyway, and then you'll have, even in an argon-filled window, it might not have argon in it anymore, and there may be condensation in between the two panes of glass in the IGU, the insulated glazing unit. But generally that's the idea. Less moisture and less heat transfer by a little bit. Well, less moisture by a lot, less heat transfer by a medium amount. Not like insane, but well worth it. And so most high performance or even medium performance windows these days will have argon. The factories that make the glass, they've gotten pretty efficient at sucking out the air and filling it with argon.
If it's only air, it's more likely to have condensation, even though it's sealed. It's an IGU.
Correct, because the air, even if it's sealed, the air has some moisture to begin with. So when it's sealed, unless there's a desiccant in there or something like that, the air will have some moisture. So even if you seal it perfectly, that moisture is in there forever.
That's true. Thank you.
Anybody else?
So is the low E film always on the second surface inside?
It's always on the second or the third. They work approximately comparably well. I think one of them works ever so slightly better than the other, but it can be on the second or the third. So it's on one of the two interior surfaces, and it almost doesn't matter which one. Although I can't remember which one it's better for, summer, winter, inside or outside. Whether it's this one or this one. But just know it needs to be in. So it's this one.
The third one coming from outside.
Yep. Okay.
And does it work basically by not letting not letting radiation or infrared
Yeah.
heat.
Yeah, it's a film that lets visible. Okay, so this is one of the, anytime you're dealing with, this is a really good question. Anytime you're dealing with electromagnetism, it's always magic. It's always kind of like, you almost have to suspend any kind of mental model and just have to trust me. But if you're looking at the color red when I draw, that's because the electromagnetic frequency of that color appears to be red to the combination of our antenna, which is our eyes, and our computer, which is our brain. And so that's why we see it as red. And in the spectrum, it's going to go from blue or ultraviolet, or say violet, what's it, or what is it, Roy G. Biv? So it's going to go from red all the way to violet. But of course it goes beyond those. That's just our visible light, that's our visible spectrum, but there's electromagnetic energy that has a longer wavelength than red, here, and has a shorter wavelength than violet, here. So here is going to be infrared, here is going to be ultraviolet, and then it's going to go beyond ultraviolet. It'll get to like gamma waves and X-rays, and beyond infrared this direction it'll go to radio waves, and the things your cell phone uses. And generally to the left of this is longer wavelengths, and to the right of it is shorter. So infrared we feel as heat. So we don't see infrared unless we have a special camera for it, but we feel it on our skin when the sun is hitting it. It's infrared energy that makes us feel warm. So heat, radiant heat travels generally in the infrared spectrum. So what a low E film does is, in that low E, this is kind of a crazy concept, but in the low E spectrum, it acts as a mirror. So to the heat, it looks like a mirror and it bounces off. So if it was 100 degrees outside and sunny, the heat would hit that mirror and bounce off, or a lot of it would. But most of the light, most of these frequencies between red and violet, most of that, but not all of it, most of that will go through, will pass through. So low E coding allows the light to pass through, but looks like a mirror to the heat, the radiant heat that comes through from the sun. And it will improve, again, it depends. In the winter it's supposed to improve, but it doesn't really that much. In the summer it will improve the performance of the window significantly, maybe 30% better, from keeping out heat or something like that. But that's if the sun's right on the window. If there's no sun, you can do better by planting a tree in the right place, or a shading element in the right place, by building a shading element, in which case the low E coating does almost no good. What were you going to say?
I was gonna ask, I'm the pain in your butt regarding the radiant barrier.
Mm-hmm. Yeah.
And so I don't understand then how the foil on the underside of Ruth's sheathing repels infrared,
right,
radiant heat coming through the roof.
Right, because it's not sun. It's not sun. How could that be? It's not sun. Is that what you're saying?
Well, I'm asking about sort of the directionality, I guess, of it, and more on maybe is low E a radiant barrier? It is.
Yes, it's a radiant barrier. I don't know if radiant barrier has a technical term that you have to be foil to be a radiant barrier, but yes, it is. As far as we're concerned here, it's all the same principle. And the reason it seems weird that foil would work in your attic is because inside the attic you can't see the sun, but it's not just about the sun. I'm looking right now at a building, I wish I could show you guys. I'm looking at a building, well, kind of craning my neck for it, and it has a wall facing west, and when I walk home, because I live near my work, when I walk home on a sunny day like today, especially a summer day where it's been baking all afternoon, if I walk home, even at night, if I walk by the brick, I can feel heat coming off the brick. Have you ever had that experience?
Yep.
Okay.
Yep.
Okay. that's where, so what you're feeling there is not the brick heating up the air and the air touching your skin. What you're feeling there is the radiant heat transfer from the brick, which is hotter than your skin. So any two bodies that see each other, where there's not like something in the way like a tree, they will exchange heat, and they'll exchange heat based on how much warmer one body is than the other, and they'll also exchange heat based on how big the hotter body looks compared to the colder body. So when I'm walking past that brick wall, because I'm close to it, it looks very big to any point on my skin. It's got a big angle of view. And so a lot of it, and it's much warmer because it's been baking all afternoon. So that heat is then gonna go onto my skin. That's why, you know, it might be a cold night and you could take a thermometer and it says that the air temperature is 40 degrees and you have a bonfire going, and near the bonfire maybe it's 50 degrees, the air temperature. But when you get next to the bonfire, you don't feel like it's 50 degrees, you feel like it's hot. And you feel like it's hot because it's not just the air that the fire is heating up, it's the radiant energy coming through the magic of electromagnetism from the fire to your skin. And the fire, as you get close to the fire looks big to your skin. And so what's happening in a roof, in an attic, in a ventilated attic, so here's our building, we'll put the radiant barrier here often. And so the sun is beating down on the roof, especially if it's black, and that roof may be 200 degrees. So the underside of that roof may be 170 degrees, that surface. So you have a 70-degree ceiling in view of a 170-degree underside of the roof. So by putting foil down here, you're allowing more of that radiant heat that would otherwise jump across from the hot surface that sees the cooler soft surface. You're reflecting some of that back up. And you're doing it for almost free. You just gotta watch out that moisture can get through. Because foil is a tricky one when it comes to moisture, because obviously if you have foil, you're not allowing moisture through. And moisture can get trapped if there's a second barrier to moisture.
So then that's why you ventilate it, right?
Well, right, in this case, the whole attic is ventilated, so if there's ever even a tiny leak in here, which there will be on a windy day, and they blow, you know, it's a sloped roof, so it relies on lapped shingles, and so sometimes there'll be wind blowing water underneath the shingle, and a tiny bit of water will get in here. But if you have ventilation at the eave of the attic, and then you have ventilation at the ridge of the attic, and there are code minimums for this, then you can dry out or if you have an attic fan, you can dry out that space. So that space is made so that it can dry out if there becomes moisture. Typically, I think we're probably more concerned with moisture coming in from the rain than we are from condensation. Condensation would come on a cold day, I suppose. And actually, on this place in the attic, there's a product that I think I included in the Amber book, but it's like little pieces of foil that you blow in. And the idea behind that is you can have the reflection, but still allow moisture to pass through so it never gets trapped.
Okay, all this is coming together for me.
Awesome.
So
I'm so happy.
my final question is, I understood the email you sent, you know, in terms of the front door and the back door, and you, in terms of heat island and this radiation problem, you want high albedo, high emissivity, but then, like, why, like grass, which is like a natural, I think, cooling mechanism in the earth, has a low albedo, right?
Maybe. But the thing is, it depends how thermally coupled it is to the building. So you can imagine a building here, and if you are thinking about your roof element as here, it's like a giant shading element that's somehow theoretically suspended, 8 inches above the roof, you can understand how even if it absorbs heat, it really is preventing radiant heat from getting to the building below. So it's reflecting the solar energy And so I'm not sure at what point, you know, when you have, depending on what kind of roof you have, but I'm not sure if when you're thinking of grass, it really is thermally coupled to the roof. I think there may be enough soil and other layers in there that you can almost think of the grass as being like a different object from a thermal point of view, from a radiant thermal point of view. But I'm not sure. I just don't know.
I guess I'm asking, like, if you had your choice of, you know, outside on your deck again, of using grass, wood, white concrete, which would, or a mirror, you know, I'm trying to, you know, and then making a generalization about albedo, and high albedo and low albedo, and, you know, heat. I mean, I would think you would want grass, as opposed to like a white, reflective surface. But this is the last little bit for me that is confusing.
Yeah, I don't know. I mean, the answer is I don't know, because a lot of it, those answers, a lot of it depends on how coupled that roof's. Like the white concrete roof, if the other side of that roof is a ceiling of the room below, that's a different answer than if the white concrete is on layers the way that wood might be. You know, if you had a wood deck that were on pedestals and it had air, you know, in between the two. So I just don't know the answer to that. I just don't know the answer to that in practice. I know that in theory, generally white concrete performs pretty well because it has a high emissivity and it has a high albedo, which means it has a small front door for letting heat in and a big back door for re-radiating the heat to the night sky. But in terms of, you know, in practical matters, well, first of all, white concrete doesn't stay white very long when it's horizontal. And if you have a green roof, then it's not like you have grass on the same surface. You have layers of perhaps trays that have air underneath them if it's an extrinsic roof, or you have maybe 7 inches of soil. And so that becomes a completely different animal. So I don't know. I think it's a fool's errand what you're going at, where you're trying to look at, and it could be that you found a question in the exam if you've taken it that took you down this fool's errand. But in general, if you get a question like that, something white and concrete would be a good solution. But in practice, I can't say without. This stuff is really difficult. This kind of radiant heat exchange is. It's not the world of high school physics. It's not even really the world of college physics. It's the world of physicists who teach at college physics. and so when it's actually applied, and you have to figure out, okay, you have wood, but you have wood over an airspace versus concrete with no airspace. I just don't know which would be better.
So just to give the so-called white concrete is not actually a concrete exposed to the sun. There is a layer of
no, we're only generally if you're asking people what the roof surface is, and you're talking about radiant heat exchange, you're generally talking about what the sun sees. The context would be what the sun sees is what you're asking.
Well,
so
isn't there an applied some sort of paint over the concrete? You
could have paint over concrete. I mean, generally you don't have concrete anyway because concrete's really porous, and so concrete roofs without any kind of membrane or bituminous material on top of it will leak. But I could imagine having concrete pavers over pedestals, and so really it's frankly it's way too difficult to talk about in the abstract, except for to say that generally white ballast or white concrete are really good as something that sees the sun as compared to other things. But for keeping a building cool, generally a green roof is pretty good too, in part because it's not just radiant heat that we're talking about, there's conductive heat losses. So there's how good of a blanket is it on top of your building. So if you're air conditioning your building and you have one roof that's concrete and another roof that's a green roof, the green roof will almost certainly have a higher R value and will lose less conductively than if you just had concrete and no insulation in it. So again, these are really, really difficult questions, and I think you're probably just going to have to let this one go. I think that would be my advice.
I'll let it go, but if you then had this, if the question was and I haven't taken the test yet, but if the question was what's more sustainable, a green landscape roof or a white concrete or a PVC or a TPO white roof,
well, I mean, those aren't really mutually exclusive. Typically, if you have a white concrete roof, you would have some kind of a membrane on top of it. But again, this is okay. So there's two different questions, right? They're studying for the test questions. There's three. They're studying for the test questions. There's use in your practice questions, and it's an itch that I have to scratch questions. And ideally, it will be all three. Like ideally, the questions you want to focus on are the ones that can benefit all three, because there are literally probably about 1,200 topics that you need to study for the test. So you might as well focus on the ones that satisfy your curiosity, help you with your progress in your career generally, and help you with the test. You can go nuts out of the 600 questions fearing that you may get a question on a given topic, and the questions that you're asking me are not ones that I can answer, not because I don't know the answer, although I don't know the answer, but they're questions that I can't answer because it's like saying, if I ask you, do I need a 2x10 or 2x12 as a structure of my deck, you need more information. And so these are difficult things to ask for in the abstract. You know, what time should you go to bed tonight? Well, it kind of depends on what time you have to wake up tomorrow, and and what your plans are for tonight, if you're out with friends or not, and so forth. So it's too difficult just to say, what time should I go to bed tonight, without me knowing way more information. But I will say that this is a complicated enough subject. I'm not feigning omniscience. It's a complicated enough subject that even if I knew way more information, it may take me a week to calculate or figure out and kind of look up old formulas. It's not the kind of thing that's beneficial for you, except for to note that if you can shade your building, that's a plus. If you can reflect heat off of your building at the roof, that's a plus. And if you can emit the heat that your building has gained over the course of the day, that's a plus. So keep those three pluses in mind, and just trust that in most cases, the question that you're asked will be sufficiently clear. Not in all cases, but in most cases will be sufficiently clear so that you'll understand what they're asking and you'll be able to answer it. And also accept that of the 600 questions on these 6 tests, you're going to have 10 questions that are not sufficiently clear. And that even someone like me who knows a lot about this stuff would not be able to answer because there's not enough information. I've come across them in the test, I've come across them in practice exams for 4.0 and 5.0, questions that I know there are 2 correct answers for, and I just know which one they're thinking about because I kind of understand what they're trying to ask, but I know that there are 2 correct answers. And that the one that they said is the best answer is often maybe only the best answer 40% of the time in my experience. But whatever, you're just gonna. This is the cost of doing business, and I know that's not what you're looking for. I'm definitely not scolding you. I'm just reassuring you that it won't be as bad as you think. These things will happen, and you may focus on them and drive yourself crazy. But in terms of the actual numbers of questions that are murky, there won't be as many as you think. Now, of those 10. Out of the 600 questions, there are 10 that are going to be murky. Of the 20 questions you remember and think about coming out of there, 10 of those will be those 10. So in your mind, half the questions are going to be murky. But in practice, it's not going to work like that. If you have a kind of a cool head about it and you really are objective, you're going to see that it's going to be maybe just a couple of % of the questions, and you're going to just have to narrow it down to 2 and do your best to answer the one that either you think is the best answer or you think they're asking for. When you're in that situation and there's one answer that's the best and one answer that you think they're actually asking for, I go with the best one. Because often the one you think they're asking for, they're not. They understand that it's not the best answer, and that's why they're asking it. They will ask questions that will seem like the intuitive one. You'll think, oh, they want me to say A, but I think the best answer is B. In those situations, they actually want to trick you into saying A, It's called a distractor option. And the best answer really is B in your head. Go ahead and answer B. I think it's worthwhile. Not every time is that going to work out, but you got to play the odds on this. Anybody else?
Mike, can I ask you a question? It's about kind of related what you were talking. What the thermal bridge, the thermal break? What is the? I mean, it always confuses me.
Yeah. So if I have a building in section, and I have a balcony coming off that building, and that balcony, the structure of the building is steel, so the steel structure comes out like this to make the balcony. If that steel is exposed to outside, and outside it's 0 degrees and inside is 70, you can imagine how that steel will get cold on the outside, and because it's the same piece of steel going all the way through, it will actually bring that cool inside the building. So that steel will look warm to the outside and cold to the inside because the temperature of that steel right here may be 50 degrees, and the temperature of the steel just inside the building may be 52 degrees. So you have a 52 degrees piece of steel inside a 70 degree building. And so your mechanical system is going to have to heat extra hard to cancel out that 52 degrees that's always coming in on that steel. And your feetsies are going to be adjacent to that floor, and so it's going to be through conduction sucking heat out of your feet because it's a cold floor. And it's going to be, if you're standing here, for all the reasons we just talked about, the cold floor looks big relative to you. It has a large angle, and that cold floor is going to be robbing your skin from radiant heat, which is a crazy concept. But so it's going to be cooling the air, it's going to be cooling your feet, and it's going to be cooling your skin that sees the floor that it cooled through conduction. So anyhow, it's bad. You don't want that to happen. So what we can do, that's called a thermal bridge, and it sounds like what it is. It's a bridge of it's a bridge of heat. So it's taking heat from inside and bringing it outside. It's taking cool from outside and bringing it inside, and it's doing that at the molecular level. In that you're cooling off a solid, and that solid, the whole piece is getting cold. Now, they make products that can break up this piece of steel right here. So it's basically a piece of plastic that you have a piece of steel here, and you have a piece of steel here, and then you have like a mounting plate of plastic, and you weld to the steel, and you weld steel to steel, and you put bolts through here and here, and then you have what's called a thermal break. And a thermal break is the opposite of a thermal bridge. It's a way of taking the structure that's continuous between the inside and the outside and disrupting it with something that's not quite as conductive. So whether that be plastic or wood. So if, for instance, you had a door here in this building, that door may have, if you have brick, that door may have a steel lintel. So you may have, say you have a wide flange, and you have your wall on top of the door, and you have your door on the bottom, right? But you can see if that wide flange, you want to, say you wanted to expose it on the inside and the outside because you like the way it looks, you can see how it's 0 degrees outside and 70 inside. That piece of steel is going to be cold, and all the time it's just going to be cold going from outside to inside. It's just going to be cold going in. So what we can do instead of using a wide flange in that scenario is if we have our wall above and we have our door below, we can use 2 C channels and a piece of wood in between, because wood is not nearly as conductive as steel. And we can bolt it together, and now it looks the same from the inside and the outside, but we provided a thermal break. So this is a thermal bridge, and this is a thermal break. And thermal breaks are meaningful. We generally don't freak out. Thermal bridges are meaningful. They in cold climates especially, they meaningfully reduce the reduce the insulative value of the skin of the building. Now,
Sorry,
yeah,
but your connectors are metal as well, so they're actually rigid.
sure, but it's all about how much the area of those connectors. So those area of those connectors relative to if they were going in. So that's what I was getting at. The goal isn't to have zero thermal breaks. The goal is to reduce the thermal breaks, in this case by 99%, and the thermal bridges, sorry. I see now you got me saying them back and forth. The goal is never to get zero. There will always be thermal bridges, the diameter of a bolt or a nail or something like that. We don't worry too much about that because that's almost impossible to deal with. Now, in a super high performance building, like a passive house building that our goal is to use maybe 10% of the energy that a typical building of its kind and its location would use, then we do worry about the bolts going through and things like that. We worry about that. In that case, we probably wouldn't have a balcony. We would just do away with the idea that it has to be exposed on both sides, and we would cover both sides by insulation, or one side by insulation, and then kind of seal it up to the door. Or maybe we'd eliminate the door because if we didn't need it, because it's hard to make a door insulatively tight. So at the scale of in the kind of mental model of the really, really tight, high performance, low energy building, we do worry about bolts going through it. We definitely do. But frankly, we worry about those more from an air leakage point of view than from a thermal bridging. But we worry about them for both. And we might eliminate the balcony altogether. But from the point of view of just a good, high efficiency, low energy building, we don't, because it's so much better than the alternative. We're not worried about a little bit of bridging going across with the bolts.
Thermal bridging is all about like heat, not moisture, right?
Correct. Thermal bridging has nothing to do with moisture, only heat. Now, but I said this.
That's where I got confused.
Okay, but that said, moisture condenses when you have warm, humid air that's touching a cold surface that doesn't let moisture through it. So, like if we think about where condensation happens, just think about where condensation happens. It happens on your soda can in the summer, that's metal. It happens on your glass in the summer of lemonade, that's glass. So it's going to happen typically on metal and glass, and it's going to happen on metal and glass that's cold. So if we have this remember we said this was a 52, just inside the building, it was a 52 degree piece of steel, and if we have a swimming pool in here and it's 70 degrees, and it's an indoor swimming pool, and we have a 52 degree piece of steel, then yes, we will have condensation on that steel, and it does become a little bit about moisture. And where that happens a lot is in parapets. So if we have the structure of our building and it's steel, and it's like this, and here's our roof in section, and so and inside we have, and so we have if our insulation goes through here, and then it also goes through here, you can see how if it's very cold out, that our steel up here will get very cold, and maybe a little bit of the steel here will be exposed to the inside. And so inside is 70 degrees and humid, and the steel is very cold. And so especially if air gets in through here, there could be condensation, significant condensation especially in a cold climate, on the parapet. So there is a moisture component to thermal bridging for sure. But those are typically edge cases. They're important enough that they may show, if you work in a mixed or cold climate, this edge case, it wouldn't be so crazy. Like it very well may show up at some point during your career that you have this problem. So it's not rare, but the better thing to focus on just don't have the thermal bridging to begin with, and then you don't have to worry about the heat loss or the condensation.